In Part 5 of Lecture 4, we will discuss top-down parsing. Parsing is the process by which we analyze a sentence or a computer program to determine what all of its parts are. This helps us understand the meaning of what it is, as we have seen in lecture number 3. In this case, you see a sentence divided into subject phrase and predicate. Then the subject phrase is divided into definite article, adjectives, and noun, and the predicate gets divided into verb phrase and object phrase. This allows us to see what role every word has in the sentence. We are looking to perform a process very close to this on a program. There are two ways of parsing a sentence. We can parse top-down or bottom-up. Parsing top-down means that we will start with the start symbol, a non-terminal that represents the entire program, or an expression, or sentence, or whatever it is that we are parsing. We then proceed through each subsidiary term, either dividing it up into smaller pieces or matching the tokens that we expect in the tree to the actual tokens that we have gotten from the scanner, and we continue until we have gone through the entire tree. We can also describe top-down parsing in terms of a tree traversal. We are, in effect, doing a pre-ordered tree traversal as we are building the tree. In general, top-down parsing algorithms are easier to understand than bottom-up algorithms, but not all grammars can be parsed top-down. However, context-free grammars can all be parsed bottom-up. Bottom-up parsing is the opposite of this. We assemble tree fragments, and when we have all the necessary components for a particular non-terminal, we assemble a tree fragment. Eventually, we have all the tree fragments assembled to give us a complete parse tree. When we talk about top-down parsing, we say that the grammar is LLK. The first L refers to the scanning being left to right. The second L refers to our assembling a left-derived tree, and the K refers to K look-ahead characters. We will concentrate on LL1 grammars because we should not need more than one look-ahead character, but this places some serious restrictions on what our grammars can contain. We need to be able to determine which one of two or more alternative derivations we will use. That means that if A can derive either alpha or beta, that they cannot begin with the same token. Also, we can have it derive an empty string, but only one of these alternatives can do this. If both of these non-terminals could derive an empty string, we could never figure out which one did. Also, if one of these two non-terminals could lead to an empty string, the other one could not derive a string beginning with whatever comes immediately after A, because then we could never tell which production was used. We also discover that not all of our grammars can be LL1 grammars, because we could not parse them correctly. If you look at the expression on this slide, and the production expression derives expression plus term, or simply term, we can't tell right away which we need to use. Obviously, we can see that we need a second term, but the computer can't tell that when it sees the first token, constant for the number 3. Both an expression and a term both begin with an identifier, a constant, or an open parenthesis, so this is not good enough. We need to change the grammar to eliminate this problem. There are two things that we can do to get rid of this problem. First, we can get rid of left recursion, replacing it with right recursion, and we can factor out common terms that the different right-hand sides have. Aho, Sethi, and Ullman's classic textbook on compiler construction addresses this problem. Any production of the form A derives A alpha or beta will produce a beta, whatever that might be, followed by a list of alphas. Let's use that to our advantage and rewrite our productions. We'll replace it with A derives beta A prime. We know it has to start with a beta eventually. then A prime will derive alpha A prime, or the empty string. This will give us what we need to parse the program. When we find the same variable at the beginning of the different alternatives for the right-hand side, we have a problem. We can't tell which of the two alternatives we need. So let's factor them out, replacing our productions with A derives alpha A prime and A prime derives beta or gamma. This will allow us to deal with the differing terms after the common term alpha. Our entire grammar is transformed. We substitute the productions with right recursion for the ones that have left recursion. And now we have gotten rid of the left recursion. This means that we can see from just one token which alternative we'll use in deriving a string from the grammar and the lookahead. An LL1 parser uses a parse table, like the one shown here, to determine which production is used in expanding the parse tree. When we start, we will use the start symbol E, and whatever our first token is. If that first token is identifier, constant, or an open parenthesis, we will look up our lookahead token and current non-terminal in the parse table and find the production is production number 1. Our start symbol will now have two children, E and T prime. If our token were anything else, this tells us that the program has a syntax error, because an expression must begin with one of these three tokens. Let's take a look at the expression in the slide, 3 times x plus y. It consists of 5 tokens, constant times identifier plus an identifier. Our parse tree is initially just the start symbol E, and our initial token is constant. Looking them up in the parse table, shown on the previous slide, tells us that we will use production 1 to derive a sentential form, an incomplete sentence, from E. E has two children, T and E prime. We will look next at T and derive a sentential form for it. We are still using the token constant because we haven't yet matched it to a token that we expect to find. T and constant gives us production 4. T derives Ft prime. These become the children of T on what we have so far in our parse tree. We now move to T's left son F and look it up in the parse table, together with our token constant. This gives us production 8. F derives constant. We now match the constant on the parse tree to our token and find a match. So we will need a new token, and we get it from the scanner. Our new token is times, and we move to F's brother T prime. Looking up T prime and times in the parse table gives us production 5. T prime derives times F T prime, and these become T prime's children. We match the times on the parse tree to our token and get a new token from the scanner, identifier. Our new non-terminal is F, and looking up F and identifier in the parse table gives us production 7. F derives identifier. We match identifier with our token and then get a new token from the scanner, plus. We now move to F's brother T prime. Looking up T prime and plus in the parse table gives us production 6. T prime derives the empty string. Since T prime doesn't have younger siblings, we go to E prime, the start symbol's younger child. We look up E prime and plus in the parse table and get production 2. E prime derives plus T E prime. We match the plus sign to the token and get a new token, identifier. We look up T and identifier in the parse table and get production 4. T derives Ft prime. Looking up F and identifier in the parse table gives us production 7. F derives identifier. Matching identifier to the token requires a new token, which is end of file, represented here as a $sign. We look up T prime and end of file to get production 6. T prime derives the empty string. And then we match end of file with E prime and get production 2. E prime derives the empty string. Our parse tree is now complete.